whether you're talking about digital code in a software program or a section of text in an English sentence or book, or the genetic text in DNA, there are vastly more ways to arrange the relevant characters that convey the information in a way that will produce gibberish than there are that will produce function or meaning.
Eden and his colleagues suspected that the genetic code faced a similar difficulty. When it came to producing new genetic information, at least enough to generate a new protein, the random mutation natural selection mechanism had to deal with what mathematicians call a combinatorial problem. In mathematics, the term combinatorial refers to the number of possible ways that a set of objects can be arranged or combined. In genetics, the combinatorial problem poses a severe challenge to the random mutation natural selection mechanism. To understand why, imagine a thief who would like to steal a beautiful new bike. All that stands between the thief and the bike is a lock with 4 dials, each marked with the numbers 0 to 9. But there is only one correct combination that will set the bike free.
The reason a bike lock works is that there are vastly more ways of arranging those numeric characters that will keep the lock closed than there are that will open the lock.
A thief without knowledge of the combination must guess the right combination from among 10 times 10 times 10 times 10 possibilities. That's 10,000 possible combinations, which usually would be more than enough to defeat a random search for the one right combination. Yet there is still a way the thief might succeed. If he has enough time to try enough combinations, he might eventually identify the right one by chance. For example, if trying each combination takes 10 seconds, then in 15 hours an especially diligent thief could try more than 5,000 combinations, or more than half of the total possible combinations. In that case, he would be more likely to succeed than to fail in opening the lock. But now imagine a much more complicated lock. Molecular biologists at the time did know that the number of possible combinations corresponding to any given sequence of DNA is extremely large and grows exponentially with the length of the molecule in question. For example, corresponding to one short protein 150 amino acids long, there are 10 to the 195th power other amino acid arrangements of that length. That's an unimaginably large number. But scientists in the 1960s didn't know how many of those arrangements were actually functional. They didn't know, in effect, how many combinations would open the lock. That didn't stop evolutionary biologists from speculating. Many argued that there must be a high proportion of functional sequences among all possible sequences, so that a random search for a new functional sequence would have a high probability of success.
The way they did that is to say, well, maybe biological sequences are not nearly as finicky, not nearly as picky about which characters are where as written language is or as computer code is. And so that's the track that they took. That maybe proteins don't really care which amino acid is where, and there's a great deal of variability, and therefore you can have the same function performed by a huge number of protein chains and a huge number of genes.
But recent experiments in molecular biology and protein science have replaced speculation with data. These experiments have established that DNA-based sequences capable of making functional proteins are in fact extremely rare among the vast number of possible sequences. Just how rare? One correct sequence for every 10 to the 77th power incorrect sequences. That's equivalent to searching for just one combination on a lock with 10 digits on each of 77 dials. To put this in perspective, keep in mind that there are only 10 to the 65th atoms in the entire Milky Way galaxy. Could random genetic mutations effectively search a space of possibilities that large in order to find even a single functional protein sequence? The building of new animals would actually require the creation of many new proteins. For this and other reasons, a number of scientists are now questioning the creative power of the random mutation natural selection mechanism. Even evolutionary biologists writing in professional peer-reviewed biology journals are acknowledging difficulties with traditional evolutionary theory. Some are willing to admit we already live in a post-Darwinian era, while others are calling for new theories of evolution. Meyer and Axe are part of a growing minority that has urged the consideration of another possibility. But how do scientists studying biological history determine which explanation is actually best? Meyer found an answer again in the work of Darwin and his contemporary, the great geologist Charles Lyell, who argued that in explaining the past, the present is the key. Lyell insisted that we should seek explanations based on our knowledge of presently acting causes, or causes now in operation. All this led Meyer to ask a critical question.
What is the cause now in operation for the production of digital information? Because the crucial question in the origin of animal life and the origin of life itself is, where did the information come from? Information stored digitally in the DNA molecule. Where did that information come from that is necessary to build these new forms of life? And I realized that the answer to that question is intelligence. The cause now in operation, the cause of which we know from our uniform and repeated experience, another key idea from Lyell, that is capable of producing information is intelligence. Whether we're looking at a hieroglyphic inscription, or a paragraph in a book, or a section of computer code, or even information embedded in a radio signal, whenever we see information, especially when we find information in a digital or typographic form, and we trace it back to its ultimate source, we always come to a mind, not a material process. So the discovery that information is running the show in life, the discovery that there are these huge infusions of information in the history of life, such as the one that occurs in the Cambrian explosion, suggests that a designing intelligence has played a role in the history of life. And it also suggested to me that it was possible to formulate a scientific case for intelligent design, that is, a case for intelligent design based on the same scientific method of reasoning that Charles Darwin had used in The Origin of Species. And so if you want to say intelligent design isn't science, you would have to say that the Darwinian argument in The Origin of Species is also not science, but no one really wants to say that. He's not using an unscientific method, he's just using a different method of scientific reasoning, an historical method of scientific reasoning, and I use that exact same method in formulating the positive case for intelligent design in both Darwin's Doubt and in Signature in the Cell.